Hello and welcome to Principles of Mathematics lesson number 11. In this lesson we're going to learn about divisibility. We'll study factors, multiples, divisibility tests for 2, 3, 4, 5, 6, 8, 9, 10, and 11, which is quite extensive compared to what is usually done. Usually most classes cover 2, 3, 5, maybe 10. We'll also look at the fact that the set of factors is finite, yet the set of multiples is infinite for any given natural number. All right, the first thing to understand about divisibility is the fact that when we say a given number is divisible by another number, we mean that when division occurs, the remainder is 0. So this is, for example, we know that, for instance, 6 is divisible by 2 because when we divide 6 by 2, we get a remainder of 0. So when that happens, we say the number 6 is divisible by the number 2. Another way of saying that is that 2 goes into 6. So you can either say 6 is divisible by 2, or you can say 2 goes into 6. Both of those meaning that when division occurs, meaning 6 is divided by 2, the remainder is 0. An integer is said to be even if it has a remainder of 0 when divided by 2. We say that it is odd otherwise. This is one way of defining an even number. Sometimes you may see the definition of an even number in this manner. You may see that an integer is even if it ends in 0, 2, 4, 6, or 8. That's another way of saying an integer is even. So when it comes to divisibility of say 18 by 3, we say 3 divides 18, or 18 is divisible by 3, for the same reason that we saw that 6 is divisible by 2, because when we do the division, the remainder is 0. And that's why we say that 18 is divisible by 3, or 3 divides 18. In a similar manner, if we say B divides A, that means basically that when you divide A by B, the remainder is 0. And the way we write that in symbolic form is we write B and then we put a bar and then A. So when you see this symbology, the way you read it is B divides A. That's how you would read that. Now, for example, 3 does not divide 25, as we know, because if you divide 25 by 3, of course, you are going to have a remainder of 1, not 0. So in this case, we say 3 does not divide 25. And of course, we would write it in this manner. We do use the 3 and the bar with 25, then we cross out the bar, meaning 3 does not divide 25. All right, and that's what divisibility means. All right, so here's a formal definition for any whole number a for any whole numbers a and b where b is not 0. We say that b divides a if and only if there is a unique whole number q such that a equals bq. All right, so if you think back to the division formula, remember that we divide a. The division formula was when we divide a by b, we get a quotient of q and a remainder of r. And the division formula was the fact that A equals BQ plus R. So notice that when we simply say A equals BQ, what we're basically saying is that the remainder of the division between the two numbers is 0. So, for example, you know that, say, 24 is divisible by 6, and alternately we can say 6 divides 24, because when we divide 24 by 6 we end up with a remainder of 0, so we can say 24 equals 6 times 4. So this is all that's meant by a statement like this, right? With no plus R being needed. That's what divisibility means. So, or that's what one number dividing another number means. It means it divides it cleanly, right? Once it divides it, there's no remainder left over. If B divides A, then B is a factor or a divisor of A, and A is a multiple of B. So, for example, when we write 24 equals 4 times 6 or 6 times 4, notice that each of these is called a factor of 24. All right? And notice that also 24 is a multiple of 6, because in this case we're talking about 6 being dividing 24, so that's why we picked that. Otherwise it can be considered to be a multiple of 4 as well, right? So we're focusing on the 6, so that's why we said it's a multiple of 6. All right, so that's how that works out. Let's see if we can classify each of these as true or false. 3 divides 12. Is that true? Of course, because we know that when we divide 12 by 3, we get a clean 4 with no remainder, so this is true. How about part B? Does 0 divide 2? Now, if you remember, division by 0 is an absolute no-no. So that means if you divide 2 by 0, you don't even get an answer, never mind whether it's a clean answer or not. This is undefined. In fact, so this is false, and in fact 0 does not divide any number. All right. How about the fact that 0 is even? Is that true? Sure, because remember, 0 is divisible by 2, and any whole number which is divisible by 2 is going to be called even. So therefore 0 is even. Remember that 0 divided by 2 is just 0. So that's a clean division, so it is even. 8 does not divide 2. What do you think of that statement? Is that true or false? Well, remember, if you're dividing 2 by 8, you're not even going to get a whole number answer, right? You're going to get 1/4, right? So therefore, that's not going to work as far as divisibility. So this is actually true. All right. How about this next part? For all whole numbers, A, 1 divides A. In other words, is A divided by 1 a whole number? Sure, because A divided by 1 is A, right? So, of course, that's going to be a whole number. So 1 goes into A cleanly. Therefore, yes, 1 does divide A. How many times? a times. For example, 4 divided by 1 is what? 4. So we say 1 divides 4 4 times. Okay? For all non-zero whole numbers, for all non-zero numbers a squared divides a to the 5. Let's take a closer look at that. So we want to see if a to the 5 over a squared can be done cleanly. Now, we know that using the quotient rule, this is going to be a to the 5 minus 2, which is a cubed. So, yes, that is going to be a whole number. If a is a whole number, like for example, let's say a is 3, right? Is 3 cubed going to be a whole number? Sure. That's a whole number too. So therefore, this statement is true because when you divide a to the 5 by a squared, you end up with a clean a cubed. Also, notice that if you want to explain it using the definition, you would say true because true for this one, right? It's true because there is a whole number, namely a cube, such that a squared times a cube equals a to the 5. And remember, whenever you can do that, you can find the number, whole number, so that you can multiply it by the first whole number and get the dividend here. Then you say that yes, it is in fact the original number does in fact divide the dividend we were looking at. All right. So how about 3 divides 6n? Well, let's look at it, right? It's very simple. Don't make a mystery out of it. Just write it down. Let's see what happens when we divide 6n by 3. Now we notice that here 6 and 3 cross out and leave us a 2 on the top and just a 1 on the bottom. So we normally don't write that 1, but if you want to, you can. So we notice that we get 2n. So of course, that's a clean division with no leftover. So yes, 3 does divide 6n. So this is true. We found out that this was true and this was true. Okay? All right, so simple but important little facts. Make sure you understand them before you move on. Okay, here we're trying to determine if 3 does not divide this expression here. Now, one quick look at the expression tells you, for example, that it's going to be even, right? For example, we know that this product here, because we're multiplying odd numbers, no matter how many odd numbers you multiply, your answer is going to be odd. You add a 1, you get an even number. Now, that could be tempting to think, oh, 3 doesn't go into it. Well, think about it. Doesn't 3 go into 12? So that itself is not enough to disqualify this as a multiple of 3, basically. So what you need to do, however, is notice the fact that you have 5 times 7 times 9 times 11 plus 1. Now, we know that in this part, we do have a multiple of 3. So we could write this part as 3 times 5 times 7 times 3 times 11 plus 1. Now, if this number were divisible by 3, we should have had a multiple of 3 here, so that then we could factor out the 3 and show that it is in fact a multiple of 3, but we do not. So therefore, this expression is not going to be divisible by 3. So this claim here is actually true. Now you can, verify the reasoning we had on a calculator by multiplying this out, adding 1 and seeing that in fact it's not divisible by 3. But the whole point of what we're doing is to do this kind of analysis without having to do the computation. All right, how about this next part? 0 divides 0. Does that seem true to you? Well, absolutely not, because if you remember, 0 doesn't divide any number, including itself. So this would be false. All right, here's a simple but important fact. For any whole numbers a and d, if d divides a, then and n is any whole number, then d divides n times a. Now, here's one of those situations where if you're just looking at symbols, this may confuse you. Just do an example for yourself, right? For example, we know that 2 divides 6, right? Now, this is telling me if 2 divides 6, then 2 is going to divide any multiple of 6, right? N is any whole number. So that means, think of it. What are some multiples of 6? Like 6 times, well, it says any whole number multiple of 6. So we can start with 0, right? What's 0 times 6? That's 0. Is this true? Does 2 divide 0? Be careful not to confuse this with 210. Yes, it does. Remember, any number divides 0. How many times? 0 times. Does 2 divide, well, the first multiple of 6 is itself, so multiply by 2, 12. Yes, it does. Does 2 divide 6 times 3? Yes, it does, right? So in general, because if d divides a, right, notice that this implies there is some number c, some whole number. So there's some whole number c such that c times d equals a, right? So if we look at n times a, that's going to be, remember, a is c times d, right? So it's going to be n times c times d, right? Which is equal to, I can write it like this, c times nd, right? So there is so the same factor c that we use to show that it must be exist, the one that whose existence is guaranteed, is also going to guarantee that NA is divisible by D as well. Okay, so also if we use the associative property, we can just write and commutative property if you want, but here we only need associative property. You can do Cn times D, and therefore we know that Na is also going to be divisible by D, and the constant that was guaranteeing that A is divisible by D multiplied by another whole number is also going to be some whole number. So this is how we would actually go on to prove a statement like this, right? This is kind of like giving you a feel for how mathematical reasoning works, right? So basically, if D is a factor of A, D is a factor of any multiple of A as well. All of this may sound very abstract, but then you look at some examples and it makes total sense, right? All right, and here we can see some properties of division, or divisibility rather. If D divides A and D divides B, then D is going to divide A plus B. So let's take a little think on that and see if it makes sense. Okay, think of what it means for D to divide A. If you remember from the definition, that means D divides A implies that there exists. Now, this backward E, I haven't introduced it to you yet, but in mathematics, it stands for there exists. So there exists some constant. I'm going to call it C1. You'll see in a minute why I want to do that. Such that there is a symbol for such that, but I don't want to make this too symbolic for you. All right, such that A is equal to that constant times, and of course the constant belongs to the set of whole numbers, right? So C1D. So if I want to get really technical, I would say there exists C1 belonging to the set of whole numbers. All right, maybe I will show you that such that it's just a backward epsilon with dots on both sides, right? So the fact that D divides A tells us that there is some constant C1 such that belonging to the set of whole numbers. This looks confusing. Let me fix it. Such that A1 equals C1, A equals C1D, right? Now, what does the fact that D divides B tells us? Where that implies there exists another constant, C2. This is why I wanted to use C1 and C2, because we're dealing with two constants. Also belonging to the set of whole numbers, such that B equals C2D, right? Now let's take a look at what A plus B is going to look like. Remember, A is going to be that first constant times D, so C1D. And B is going to be that second constant times D, right? So now, watch what happens. If we factor out the D, right, we get A plus B equals C1 plus C2 times D. But remember, C1 was just some constant, C2 was some, constant whole number. So by the closure property of the operation of addition over the set of whole numbers, we know that this is going to be some constant whole number, right? So what does that mean? That means A plus B is some constant times D. So that tells you, therefore, this triangular formation of dots means therefore. Therefore, D divides A plus B as well. Okay? So here's how a quick way of just verifying that. Just using common sense and everything that you've learned. This is very elementary material, right? But it shows the clarity of thinking. Now, be really careful. These are one-way conditionals, right? These are not biconditionals. This doesn't mean it works the other way as well. Just because of the fact that a number divides a sum, that would not imply that it divides either one. I want you to think for a minute if you can come up with an example of where this could be true, that a number divides a sum, but it doesn't divide the individual numbers. Think for a minute and come back. All right, so notice that we're saying the fact that a number divides a sum does not imply that the number divides each of the two terms in the sum, the two numbers in the sum, right? The two addends. So notice here, does not imply. So here's the example. I'm not sure what yours was, but here's mine. Now, I know that 3 divides 2 plus 4, doesn't it? Because 2 plus 4 is 6. Doesn't 3 divide 6? Yes, it does. However, 3 does not divide 2, and 3 does not divide 4. So be very careful in turning these conditionals and looking at the converse, because the converse of these conditionals is often not true. All right, so now it's saying if D divides a first number A, but it doesn't divide a second number B, then it's not going to divide the sum, okay? And you can see by the reasoning we used here, you should be able to see why that happens. Think about that, okay? If D divides A and D divides B and A is greater than B, then D divides the difference as well. The proof of that fact would be very similar to this, okay? And here you would end up with just C1 minus C2, and because of the fact that you have a whole number that's bigger, this would end up being some positive whole number as well, and then you would establish your fact. Now, if D divides A and D does not divide B, even if A is greater than B, D is not going to divide the difference. And if D does not divide A, but D does divide B, even if A is greater than B, it still is not going to divide the difference. All right, some properties of divisibility, actually. All right, so let's see if these are true. These statements we're going to classify as true or false. If 3 divides x and 3 divides y, does 3 divide the product? Yeah, that's actually much simpler to establish than with the sum, right? So think about it. 3 divides 6 and 3 divides 9. Does that imply that 3 divides 54 or 6 times 9, right? So again, you can actually do this with using a formal proof, but just as a demonstration here, yes, the fact it does hold, right? Notice that's just 2 times 3, and that's 3 times 3, and when you multiply them, that product is definitely going to have a factor of 3 in it, so therefore 3 is going to go into the product. Kind of in a nutshell how you would go about proving it, right? All right, so the first part is true. How about the second part? 3 goes into a sum. Does that mean 3 goes into each number? Remember, we just spoke extensively about that, and we in fact had an example showing that this in fact is false, because if you remember, 3 goes into 2 plus 4, but 3 does this does not imply that 3 goes into 2 and 3 goes into 4, right? All right. How about this one? If 9 does not divide the number, that means 3 does not divide the number either. What do you think of that? Well, not necessarily true, right? Notice that 9 does not divide 3, correct? But 3 divides 3. So this statement here is false. All right. So these are really good exercises because they really make you think, and that's the whole point of this class, to awaken the part of your mind that may not be always super active. And this will, in fact, this kind of reasoning doesn't just have benefits for your performance in this class. I mean, this kind of reasoning, this kind of awakening the logical part of the mind is going to help you in all types of decision making situations. So uh, think of that as you proceed, and that should lessen the pain of having to put up with mathematical logic, right? Okay, let's go ahead and go forth. Oh, here's one little thing to keep you motivated and going. Research has shown that the more mathematics you take, you end up with the more money that you make. So, of course, unless you become a mathematics teacher, right? So, anyway, but you can look that up. So there has been a correlation, a significant correlation, enough to make it to an article. So, all right. So let's move on. Actually, before we do, let me ask you: would this have worked, this last one, if it were the other way? What if I add a part D and say if 3 does not go into A, then 9 does not go into A? I think you will if you think about it a little bit, you realize that is in fact true. Okay, so if 3 doesn't go into a number, 9 will definitely not go into the number. So it works this way, but not the other way around. All right, sometimes you can tell if a number is divisible by another number by just looking at it, right? Like you look at 1734, you know it's going to be divisible by 17 because basically you can always break it up as 1700 plus 34, and you know 17 goes into 1700 for sure, and it also goes into 34. Therefore, 17 is going to go into the sum, right? Remember, if 17 goes into one number and 17 goes into another whole number, then 17 should go into the sum, right? We've seen that already as one of the properties of divisibility. So now here we know that 17 goes into 1700, and we know that 17 goes into 34. Therefore, 17 should go into 1700 plus 34, which of course means 17 goes into 1734. All right, there's that. All right, one way to test divisibility is if you have a calculator that's capable of doing this, you could use what's called the integer division feature of that calculator. Now, the one that I have been recommending to you is this freely available HP Prime graphing calculator. Now, on this calculator, you do not have actually a integer division button that's very clearly obvious, right? But it is in there. This is quite a powerful machine, and you just need to know the command. Okay, so the command that HP uses is int IQUO, and then if you want it to show you the remainder as well, you would put REM, and then you would want to put within parentheses, so click the parentheses and then type. So let's say we wanted to do this number, right? 1734. So you put the dividend first, then you put the divisor, and then you hit enter. Okay, so now this result is very helpful because it tells you 17 goes into 1734 102 times with a remainder of 0, right? So you know that of course when the remainder is 0, there's divisibility, right? So 17 goes into that, right? So this IQUOREM, you really better try to type with your keyboard, because if you want to use the keyboard on the calculator, you have to put shift the characters and then as far as I know, it only takes one character at a time. So it's a little bit of a pain to get all those letters in if you're using the keyboard on this, right? Because it lets you take just one character at a time. So not the best option. All right, so you can get out of that by pushing escape on your keyboard, computer keyboard, okay? So it's a very, very handy tool, right? So now, and the nice thing is on your computer, you can copy the IQ, you know, OREM. So integer quotient with remainder. That's what that means. Integer quotient with remainder. If you understand what it means, it'll be easier to remember it, right? So what I can do is I can just write that and I can just copy that, you know, using the copy feature of your, let's see if it copies that. If not, you can always just type it in the notepad. Yeah, I think it did copy it. Let's see what it copied. Yeah, so it's copied it. Okay, so whatever, when your cursor is inside this text entry area, whatever you copy gets copied to the clipboard, right? So this is really nice because now you can either use open close parentheses or you can just do this on the calculator itself because it'll do both for you. So this is really nice, right? Like let's say you want to know if 198 is divisible by say 7, right? So you just type that and you can see it is not, because 7 is going to go into 198 28 times with a remainder of 2. So divisibility requires a remainder of what? 0. Okay, there's that little tip for you. All right, so here are the three of the important divisibility rules. A whole number is divisible by 2 if and only if its units digit is divisible by 2. That is, if and only if the units digit is even. Meaning what? Let's go with another if and only if. This time we'll do it symbolically. We'll say if and only if the units digit is 0, 2, 4, 6, or 8. All right. A whole number is divisible by 5 if and only if its units digit is divisible by 5. And that means what? That it only if the units digit is 0 or 5. Okay? Sometimes instead of saying if the units digit is, we say if it ends, because we consider the rightmost digit in a number to be the ending digit, right? A whole number is divisible by, so remember, divisibility by 5, super easy. If a number ends in 0 or 5, it's definitely divisible by 5. What kind of numbers are divisible by 10? Not as many. The ones that are divisible by 10 only end in a 0, okay? So only if a digit, if a number ends, meaning if it has a unit digit that's a 0, is it divisible by 10? Few more divisibility rules. What kind of numbers are divisible by 4? Well, not as easy to determine as it is for 2, but not that hard either. As long as the last 2 digits of the number form a number that is divisible by 4, then it's divisible by 4. For example, let's say I give you some really large number, 3, 2, 7, 9, 5, 4, 9, 2, 1, 6, right? I mean, that's a huge number, but you don't need to sit there and divide it by 4 to see if it's divisible by 4. All you have to do is look at the last 2 digits. Does that form a number that is divisible by 4? Yes. Therefore, the whole number is divisible by 4. Same goes with divisibility but by 8, but you have to add another digit. So if the last 3 digits of a number are divisible by 8, then the number is divisible by 8. The whole number is divisible by 8. So as an example, so let's say, again, we have quite a large number, 7,900, and say 56,024. Right, now look at, all you got to do to see if the number is divisible by 8 or not, look at the last 3 digits, right? Well, 0 to 4, that's just 24, right? Is that divisible by 8? So you know for sure that the number is divisible by 8. You can, of course, verify by doing the division. So 7, 9, 5. But why don't we use our rule, right? Why don't we use our IQRM rule? So we want to see what happens when you divide 7, 9, 5, 6, 0, 2, 4. And remember, you have to put comma and then the divisor. So we want to know how this does with 8, right? Notice that it is divisible because here's the quotient and there's the remainder. So because of that, you know it's divisible by 8. All right. So these, I think they're pretty obvious. I mean, if you wanted some examples on these, of course, any even number for 2, for 5, any number that ends with 0 or 5, right? So say 3, 9, 5, 6, 0. There, I don't have to do much work. I know that number is going to be divisible by 5. How about 8, 8, 8, 8, 5? Yeah, doesn't matter what these numbers are. I'm looking at that last digit, right? The units digit. Is it a 0 or a 5? Then it's divisible by 5. And by 10, very simple, right? So is this one divisible by 10? Yes, because it ends in 0. Is this one divisible by 10? No, because it doesn't end in a 0. So that's the only criteria there. All right, let's see if this number here is divisible by 2, 4, and 8. Now, we know that it is divisible by 2 because it ends with an even number, right? So 2 does divide 97,128. And how about 4? Does 4 go into it? Yeah, because the last 2 digits are 28, which is divisible by 4. So we say 4 does divide 97,128. And how about 8? Well, the question is 128 divisible by 8? Well, you can just calculate it, or you can do the prime factorization. There are different ways you can go about it, right? Right now, for the purpose of efficiency, we'll use a calculator. So here we're just going to go 128 divided by 8, 16 times. So therefore, yes, the last 3 digits form a number that's divisible by 8. So therefore, 8 divides that number as well. You should be comfortable with both types of language. 2 divides 97,128, or 97,128 is divisible by 2. 4 divides the number, or the number is divisible by 4. 8 divides the number, or the number is divisible by 8. They mean the same thing. All right, how about this number? Is this divisible by 2? Yes, it is, because it ends with an even number, right? How about 4? Well, the last 2 digits form 26, right? And 26 is not divisible by 4. So therefore, the number itself is not divisible by 4 either. And how about 8? Well, if it's not divisible by 4, it's definitely not going to be divisible by 8, right? So therefore, but just looking at the last 3 digits as well, you can see 0.26 is just 26, right? And it's not divisible by 8. So therefore, 8 does not go into 83,026. So here's a nice visual that shows us this relationship. Notice that the largest set here is the numbers that are divisible by 2. Smaller than that is the set of numbers that are divisible by 4, right? So that means there are many numbers that are divisible by 2 that are not divisible by 4, right? And much smaller than that are the numbers divisible by 8. So there are numbers that are divisible by 2 or 4, but not by 8, right? So there we go with this nice Venn diagram explaining this to us. So more restrictive, less restrictive, right? From more restrictive to less restrictive. Okay, we're going to add two other divisibility tests to our repertoire, and that is divisibility by 3 and divisibility by 9. They're both very easy. They are both true if the sum of the digits is divisible by the given number. So a whole number is divisible by 3 if and only if the sum of its digits is divisible by 3. Same goes for 9. A whole number is divisible by 9 if and only if the sum of the digits of the whole number is divisible by 9. So let's look at the 3 one, for example. So let's say I asked you whether 126 is divisible by 3, right? Well, all you have to do is add the digits. See? Now, a lot of students incorrectly think the number has to be odd or this or that. No, none of those things. This is the simple rule. Add the digits, okay? 1 plus 2 is 3 plus 6 is 9. So 1 plus 2 plus 6 is 9. Now, and we know that 3 divides 9. Therefore, 3 divides 126. Okay? Just like that. How about divisibility by 9? How about that same number, 126, right? Again, 1 plus 2 plus 6 is 9, right? Notice that 9 does divide 9. Every number divides itself. How many times? Once, right? Therefore, 9 also divides 126, right? Now, remember, this is not always the case. There are many numbers that are divisible by 3, but not by 9. Here's a simple number, 6. 3 does go into 6, but 9 does not go into 6. So be very careful in making generalizations. All right, here we want to see if 1002 is divisible by 3 and 9. Now, we add the digits, right? And we get 3. So we know 3 goes into 3, and therefore it goes into 1002. But 9 does not go into the sum, which is 3. Remember, 9 doesn't go into the sum, therefore 9 doesn't go into the number itself. Only if 9 goes into the sum would it go into the number itself. How about this particular number, 14,238? Is it divisible by both 3 and 9? Well, when you add the digits, you get 18. Now this time, both 3 goes into 18 and 9 goes into 18. So both of them are going to be divisible. Both of them are going to divide 14,238. In other words, this number is indeed going to be divisible by both 3 and 9. All right, I brought this next problem into a notepad so we can have some extra space into a whiteboard. It's one of those problems written by someone with a lot of time on their hand, I guess, but it's quite interesting, and it gets us to practice some nice facts about divisibility. So we have a store manager has an invoice for 72 calculators. The first and last digits on the receipt are illegible, and the manager can only read those digits, right? We want to know what are the missing digits and what is the cost of each calculator. Seems like a daunting task, but you can see that divisibility will come to the rescue. All right, so we have two missing digits, right? So let's go ahead and give them some names. So let's call the first one x. So we have x 6 7.9y. Now remember, this is in dollars, right? It would be nice if I didn't have to work with the decimal point. So I'm going to go ahead and say this many dollars is equal to, just multiply by 100, which is going to move the decimal point 2 to the right. So I'm just going to get x 679y, right? And this one is in cents. Okay. Now, obviously 72 calculators were purchased, right? So this number must be divisible by 72. 72 must divide x 6 7 9 y, right? But notice that 72 itself is 8 times 9, right? So what does that tell you? That tells you that both 8 should divide this number and 9 should divide the number. Now, what does it mean for the number to be divisible by 8? That means these last 3 digits, right, should form a number that is divisible by 8. So, well, let's see what that digit could be, right? Well, let's go ahead and bring up our calculator, right? So let's try 790. See if that's divisible by 8. It's not. So we'll try 791. Now, we know that's not going to be divisible by 8 because it's not even, right? But just to satisfy the curiosity, we'll go ahead and notice that. Now, what about 792? That one is, okay? And you can try the other digits as well. Of course, you can leave out the odd ones. So let's just try the even one. 794 is not divisible by 8. How about 796? Is not, and 798 is not either. So the only possible value we could have for y is 2. So because 8 goes into 792, therefore y must be 2. All right, so we're getting a little bit closer, right? So we know that, so we took care of this part, so we know that 9 must go into x 6 7 9. Now we can go ahead and write down what we know 2 has to, the y has to be, right, which is 2. So 2. Now for 9 to go into this, that means 9 has to go into the sum of the digits, right? So that means 9 must go into x plus 6 plus 7 plus 9 plus 2, right? Now that's what? 13, 22, 24. So that means 9 must go into x plus 24, right? So 6, make sure we did it correctly. 6, 13, 22, 24. Okay, so now we have to see what values for x, remember digits 0 through 9, would make this a multiple of 9, basically, right? So that 9 goes into it. So obviously we know 9 doesn't go into 24, so 0 is not going to work. We know it doesn't go into 25, that's not going to work. Into 26, it doesn't go. We know 9 goes into 27 3 times, right? So there's one possibility. How about does 9 go into 28? No, it doesn't. Into 29? No, it doesn't. So the only possible value for x is 3, because that's what makes 24 plus x, so that 9 goes into it, right? So we know that 9 goes into 27, therefore x must be what? 3. So now we have both x and y, so we can go ahead and fill them in to the number, right? So x is the first number, the first digit here on the left. So 3, 6, 7.9, and we know that y is 2. So this is how much the manager spent, right? They also know what is the cost of each calculator. Now all we have to do, this is the total, so cost per calculator is just going to be the total divided by the no. So this many dollars divided by 72 calculators. So we're going to get the unit cost by just handling that division. So 367.92 divided by 72. So we get $5.11 per calculator. All right, so a beautiful problem when it comes to applying divisibility and making sure that you understand it. So again, if you didn't come up with it on your own at the beginning by pausing the video, make sure that you pause it now and try to see if you can work it all the way from beginning to end without any help. That's when you know you've gotten close to really understanding it, right? So that if you fail at doing it once, no problem. Do it again, until you're comfortable enough to where you can just do it without a whole lot of questions in the middle of it, all right? So that you've gotten really comfortable with the concept. All right, 2 more divisibility rules for us, and that's going to bring us to the end of the lesson. So divisibility by 11 is quite elaborate. Most people don't know this or use it, but it's good to know. A whole number is divisible by 11 if and only if the sum of the digits in the places that are even powers of 10 minus the sum of the digits in the places that are odd powers of 10 is divisible by 11. So what you want to just as a mnemonic keep in mind is that the sum, this is a notation that we use for summation, right? So the sum of the digits in the even powers of 10, right? So you just want to keep something like this in mind, minus the sum of the odd is a number that 11 goes into. So if that happens, then 11 goes into the particular number. All right, we're going to look at an example in a minute. It'll all make sense to you. Just keep on, keep that in mind while we move on to this. a whole number is divisible by 6, and this is going to make a lot of sense to you. Think about it. What is 6? That's 2 times 3, right? So if it's divisible by 6, if and only if it's divisible by both. That's the key word. Has to be divisible by both 2 and 3. If both 2 and 3 go into a number, then the number is going to be divisible by 6. All right, here's our final example. We have this monstrous number, right? 57,729,364,583. We want to know if this number is divisible by each of these as our final practice in this area. So some of them are very easy to answer. Notice that 2, we know that it's not, because the units digit is not even. 5, it's not, because we know that the units digit is not a 0 or a 5. 8 is not, because the last 3 digits don't form a number that's divisible by 8. It's not even, right? So no. 10 won't work because the number doesn't end in 0, and therefore it is not divisible by 10. All right, so now we know that it's not divisible by 2. That's enough to tell me that it's not going to be divisible by 6, because remember, to be divisible by 6, it has to be divisible by both 2 and 3. So 6 is out. For 3, we have to find the sum, right? So there's no cheating around that. So we're going to go ahead and just get busy and add all the digits. So 5 plus 7 plus 7 plus 2 plus 9 plus 3 plus 6 plus 4 plus 5 plus 8 plus 3. As I've told you before, after you input something like that, always double check, because it's so easy to make an error, right? So let's see, 5, 7, 7, 2, 9, 3, 6, 4, 5, 8, 3. It looks pretty good. So we end up with 59 for the sum of the digits. Now, that is not divisible by 3. How do we know? Well, what's 5 plus 9? That's 14. That's not divisible by 3. So therefore, the number is not divisible by 3. But notice that once you find the sum, you also take care of 9, because 59 is not divisible by 9 either. So therefore, the number is not divisible by 9. So 2 more that are out. So let's face it, they probably gave us this example just so that it works with 11, right? Let's see. So remember, for 11, you want the sum of the digits that are even powers of 10 minus sum of the digits that are odd powers of 10 to be divisible by 11. In other words, 11 should go into that sum. So let's look at so we're going to start. So remember, the first digit on the right, this is the 10 to the 0 place, right? The next one is 10 to the 1 place. The next one is 10 squared place. The next one is 10 cubed place, right? So, like so, right? So let's be efficient, and I'm just going to put the powers of 10 above each of the numbers to keep this clean, right? So in other words, the exponent only, not the power, the 10 itself. So let me use red for the even one. So I know 3 is 10 to the 0. Let me make this a little bit thinner. Okay, that's better. All right, so 3 is the 10 to the 0 term, 5 is the 10 squared term, 6 is 10 to the 4 term, 9 is the 10 to the 6 term. Just, we're just skipping one, right? Makes sense, right? And then 7 is the 10 to the 8, and 5 is 10 to the 10 term, right? Now, in green, below the odd powers, 8 times 10 to the 1, right? So that's a 1. So let me make that thinner too. Oh, that's too thin. Come on, cooperate too. Okay. So 8 is the 10 to the 1 term. 4 is going to be the 10 to the 3 term. 3 is going to be the 10 to the 5 term. 2 is going to be the 10 to the 7 term. And 7 is going to be the 10 to the 9 term, right? Okay, so remember, you want the sum of the digits that are even powers of 10. So we're going to add starting with 0 going to 5 or going the other way. It doesn't make any difference. Let's start here. So the 10 to the 10 one is 5. The next even power of 10 term is 7. The next one is 9. Next one is 6. Next one is 5. Next one is 3. Minus, now we want the sum of the the odd powers of 10. So starting with 9, so the 9th power, so we get 7 plus, the next one is 7. I'm sorry, the next one is 2. I mean, the 7th, the power of 10 is 2. For the 5th power of 10 term, it's 3. And then for the 3rd power of 10, it's 4. And for the 1st power of 10 is 8. So we take care of this sum. We can do it by hand, or we can just punch it into a calculator. So we have 5 plus 7 plus 9 plus 6 plus 5 plus 3. So that's 35 minus went to the wrong place, did that. Here we go. All right, my touchy screen. All right, now now we want 7 plus, we're handling this sum now, right? So plus 2 plus 3 plus 4 plus 8. And that ends up being 24. Now 35 minus 24, oh, look at that. Isn't that nice? 11. Now 11 divides itself, therefore 11 is going to divide, I'm just going to call it n, okay? So 11 divides n. All right, so there's that. All right, that's pretty much it for our lesson. Make sure you practice some of these, and you can always try your own numbers, right? Write a random number, check it out, see if it's divisible by 11 or not. All right, let's do our usual tradition and do a few homework problems now. All right, on this one, I just want to give you a hint. You want a number that's divisible by 2 and 3 but not 5. This should be easy to find. Pretty much any many multiples of 6 will satisfy that, right? uh, you want a number that's divisible by 2 and 4 but not by 8. These kinds of numbers exist as well, but they're a little bit trickier to find than the first case, but there are plenty of them available. One of the things you could do is see the choices that are given and then kind of test them out like that, but that should not be difficult to find. How about a number that's divisible by 5 and 10 but not by 2? Think about that one a little closely. And I think if you think hard enough, you'll see that that's not possible. There's the hint on that. All right, here we have a nice problem about divisibility. We want to see if these statements are true or false. If it's false, we want to show a counterexample that proves it false. How about part A? If every digit of a number is divisible by 3, then the number is divisible by 3. Does that make sense to you? For example, let's look at an example of what they're talking about. Like, let's say 6, 3, 9. Do you think that number should be divisible by 3? Of course, because if each digit is divisible by 3, that means the sum of those numbers that are divisible by 3 is also going to be divisible by 3, right? And therefore, remember we had a rule that said if D divides A and D divides B, then D divides A plus B. I want you to think in that kind of direction, and you'll see what I'm talking about here. All right, so the first one should be a true statement. How about the second one? If a number is divisible by 3, then every digit of the number must be divisible by 3 or is divisible by 3. They're turning things around now. So we have a P implies Q, which is true. And now they're giving you Q implies P, and they're saying, is that true? Well, remember, oftentimes, this is called the converse, right? For many of these statements about divisibility, the converse turns out not to be true. This is an example. Think about it. Here is a number that's divisible by 3, right? Does that mean every digit is divisible by 3? Obviously not, right? So just think of a nice counterexample to use. A number is divisible by 3 if and only if the sum of the digits is a multiple of 3. Well, I think that's a pretty simple part, so I'm going to leave that for you. And I'm not even going to tell you it's true or false, but I'm just going to say, think about it. It's very simple to answer. Just think of what it means to be divisible by 3, and it should pop at you. All right, here's a nice problem when it comes to understanding divisibility by 9. We say if the 5-digit number AA448 is divisible by 9, what digit does A represent? Okay, so remember what divisibility by 9 means. It means 9 also divides the sum of those digits, right? So A plus 4 plus 4 plus 8, right? That means 9 divides 2A plus 4 and 4 is 8 and 8 is 16, right? So again, a lot of this material becomes really easy if you become really organized about your approach. So basically, I want to test some values now, possible values for A. What are the possible? A is just a digit in a number, right? So it can be anywhere from 0 to what? To 9, right? So here I'm going to make a table. I'm going to say A. Then I'm going to look at 2A, and eventually I want to get to 2A plus 16, right? Remember, obviously, the possible values for A are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So Now, if I plug in 0 for A, right, I get 2, for 2A, I get 0. So 2A plus 16 will be 16. Now, we know that 9 doesn't go into 16, so A can't be 0. Now we plug in 1, so we get 2 times 1 is 2 plus 16 is going to give me 18, right? Now we know that 9 goes into 18, so A could be 1, right? So just to make sure that there are no other possible choices for A, you quickly go ahead and finish the rest of them too. 2 times 2 is 4 plus 16 is 20. We know 9 doesn't go into 20, so it won't go into that number. 3 times 2 is 6 plus 16 is 22. You get the idea here. That's not going to work either. 9 doesn't go into 22. 8 and 16 gives me 24. Notice the pattern. The next one is going to be 10, 12, 14, 16, 18, and these are going to go up by 2 as well, right? So and 10 and 16 is 26, 28, 30, 32, and 34, right? Notice that the only one in this bunch that's divisible by 9 is 18. So the only possible choice for A would be A equals 1. All right, again, another good problem when it comes to understanding divisibility by 9. All right, here's a problem that may not appear to be about divisibility, but it's all about divisibility. The bookstore marked some notepads down from $2, but still kept the price over $1. It sold all of them. The total amount of money from the sale of the pads was $31.45. How many notepads were sold? So I will give you a hint here, and you should be able to finish it. Basically, think of the 31.45 as, this is $31.45, but it's much easier if you look at it as cents. So 3,145 cents. Basically, what you want to do is you want to go ahead and see which numbers that is divisible by. Use all the divisibility rules. You may end up with having to go beyond even the divisible the numbers we've discussed. Like we've gone up to 11, right? You may need to go above to 13, 15, 15. Try all those 17, etc. 15, of course, you don't need to do, for example, because if it's not divisible by 3 or by 5, it's not going to be divisible by 15, right? So work your way up until you will realize why these answers are the way they are. So try this and finish it before you leave this page. Okay, on this one I have a hint for you. You have a football game you're dealing with, and you know that if you watch football, you know this. If you don't, no problem. You don't need to know football to be able to do this problem. A touchdown with an extra point is worth 7 points, and a field goal is worth 3 points. Suppose that in a particular game, the only scoring done by teams are touchdowns with extra points and field goals, okay? So the hint is that, remember, the only numbers you're going to be using for a final score are going to be 3 and 7. This is to simplify the scenario, because normally you would a score of 6 for a touchdown would be possible as well without the extra point, right? So here you don't need to worry about those scenarios. You're only dealing with 3s and 7s. So make sure when you answer these questions, you keep that in mind. So any score should be some combination of one or both of these, right? Or more than one of these with more than one of those. That's how you're going to get your proper scores. And once you keep that in mind, this becomes a relatively easy question to answer. Just there may be a little bit of busy work involved. You have to try different combinations, but very doable. All right, here we have a student, Amy, who seems to be confused about what it means to be even or odd, because she claims that 10 is both even and odd because it's divisible by the even number 2 and the odd number 5. Now, how would you respond? Clearly, you need to describe the divisibility rules for Amy and explain to her that an even number is a number that has a remainder of 0 when divided by 2, and an odd number always has a remainder of 1 when divided by 2. Think about that fact and try it out for yourself. Just write any odd number down and divide it by 2. You're going to see that there's always going to be a remainder of 1. And of course, 10 has a remainder of 0 when divided by 2. It is even and therefore not odd. All right, I think that'll be a good place for us to call it the day. It's kind of a long video, so go ahead and take care of yourself, and we'll see you for the next lecture.